All right, welcome to The Explainer. Today, we're unlocking the secrets of one of the most important codes in digital history, the Data Encryption Standard. You'll probably know it as DES. It's the algorithm that really set the stage for all of modern digital security. So let's just start with the basic problem here. How do you send a message, any secret message, across, say, the internet, and make sure that only the right person can read it? This is the whole puzzle that cryptography is trying to solve. Okay, so to tackle this, computer scientists came up with basically two main ways to do it, two different blueprints for creating a digital secret code. And of course, each one has its own pros and cons. So on one side, you've got what are called stream ciphers. The best way to think about these is like a continuous, real-time scrambler. They're super fast, which is awesome for stuff like streaming video. And then on the other side, you've got block ciphers. Now these are more like a series of, let's say, high-security lockboxes. They take your data in chunks, right? And while they might be a little bit slower, they mix up the message so thoroughly that they're way more resistant to somebody trying to break in. And DES? Yeah, that's a classic block cipher. So what actually makes one of these digital lockboxes secure? What's the magic sauce? Well, it really boils down to two key ideas, kind of like a secret recipe that was first laid out by the father of information theory himself, the one and only Claude Shannon. Okay, so ingredient number one is called confusion. And the whole point of confusion is to make the relationship between your secret key and the final scrambled text just as complex and tangled up as humanly possible. Basically, you're swapping bits of data for other bits. It makes it a total nightmare to try and reverse engineer if you don't have that key. All right, ingredient number two, diffusion. Now, this one is all about spreading the information from your original message far and wide throughout the scrambled version. The idea is, if you change just one tiny little bit of your original message, diffusion makes sure the scrambled output changes dramatically. This completely hides any patterns an attacker might be looking for. It's brilliant. So with these two big ideas, confusion and diffusion in mind, the world really needed a standard, a trustworthy lockbox that everyone, we're talking banks, governments, everyone could use to protect their data. And this need is what gave birth to a true legend in the world of cryptography. So get this, back in the mid-70s, the US government did something pretty revolutionary. They basically put out a public call saying, hey, we need an encryption algorithm that anyone and everyone can use. And you know who answered? IBM. They came in with a design based on their own cipher called Lucifer. And by 1977, the Data Encryption Standard was official, and it just exploded, quickly becoming the go-to benchmark for secure communication all over the world. Right, so since DES is a block cipher, it was designed to work on these fixed-size chunks of data. It grabs your message and processes it in these tidy 64-bit blocks. But, and this is important, the size of that data block, that's really only half the story. Yeah, the other half is the key. And this is where things got a little controversial. See, the final standard called for a 56-bit key. Now, that was a lot shorter than what IBM had originally proposed. And this reduction? It was done at the request of the National Security Agency, the NSA. This immediately sparked fears that the whole thing was intentionally weakened, that it had a back door so the US government could crack messages while still being just strong enough for commercial use. So, okay, how does this legendary and, pretty controversial lockbox actually scramble your data? Let's take a peek inside the DES scrambling machine. Well, it all kicks off with a really simple division. That 64-bit block of your message, it gets split right down the middle into two 32-bit halves. And that simple split is what sets the stage for this really interesting dance between the two sides. The whole process basically happens in three main stages. First up, you've got an initial shuffle. They call it a permutation of all the bits. Then comes the real magic. 16, count them, 16 rounds of some seriously intense mixing and scrambling. And then finally, there's one last shuffle at the end to lock it all up into the final encrypted text. Now, here's a really critical detail. It's not like you're just using the same lock 16 times in a row. Nope. Instead, that main 56-bit key is used to generate 16 totally different, unique subkeys, one for each of those rounds. This whole multi-stage approach is what makes the code so incredibly hard to pick. And this is where those secret ingredients we talked about, confusion and diffusion, really get to work. So in every single round, you have these special components called S boxes, that's for substitution boxes, and their job is to swap out bits to create all that confusion. Right after that, you've got P boxes, permutation boxes, and they shuffle all those bits around to create the diffusion. Now, the exact design of these S boxes was actually kept secret, which you can imagine just added to the whole controversy. But the way they work together, it's really a masterclass in cryptographic design.
I mean, DES was an absolute titan for years, but as computers got exponentially faster, that 56-bit key started to look a little vulnerable, to just brute force attacks. But the solution wasn't to just toss the whole thing in the trash. Instead, the community came up with this really clever way to make it way, way stronger.
In this formula right here, this shows the genius of what's called triple DES. So what you do is, you encrypt your text with a first key, then you decrypt that result with a second key, and then finally, you encrypt that result again, either with the first key or even a third one. This whole encrypt, decrypt, encrypt sequence, it was just a brilliant move. So by basically tripling down on the process, triple DES massively extended the life of this algorithm. For years, it became the new go-to standard for banks and other really critical systems. But I think what's even more important is that it proved the core design of DES was just so solid, so robust, that it could be the foundation for security for a whole other generation. The story of DES, from its kind of controversial birth all the way to its clever second life with triple DES, it's just this powerful reminder that the race between the code makers and the code breakers, well, it never, ever ends. And it really makes you wonder, right? As we're now heading into the age of quantum computing, what on earth is the next generation of unbreakable codes even going to look like?